All right, good morning. Got your exams back. So the average was a 92, so you guys did quite well. So congrats overall. So we'll go over the solutions here, clear anything up that might have been confusing, and then probably have time to start on the kind of biological oxygen demand, so that by the end of Tuesday, you should have most everything you need for the homework. That way you'll have plenty of time to deal with that. So I'm gonna hand these out. So Abby. Caroline. Aaron. Tucker. Alex. Francesca. Sydney. All right, and if you watch this later, I've got your exams. I'll keep them with me in the next several lectures. So I should have them with me if you come get them later. Okay. All right, so since you all did pretty well, I'll ask that if you did have some confusion on a problem, slow me down. So otherwise I'll try to kind of go a little faster than maybe I would normally. Okay, so problem one, we had bromine and chlorine. They're essentially quite similar with a bit of different reaction kinetics. And I would say the last question on this problem was really the one that I was hoping for a little better of an answer, and I went lenient on everybody. So I'll explain that in a few minutes. But you could have added a quantification to that answer. You could have made it quantitative, and I'll walk you through that. Okay, so bromine and chlorine, they're very similar. Bromine is sometimes used for swimming pools. It's as we see from the problem, we've got a different Ka value. That means a different equilibrium point for the pH. And we also have different rates for inactivation of a given pathogen. In this case, I think we're doing, is it Giardia or maybe just some generic pathogen. Okay, so we've got a little table. Part A says, how long would it take to remove 99.8% of viruses from the swimming pool if 1.5 milligrams per liter of HOCl was applied? And so I suppose there was perhaps a little bit of room for confusion here. I was meaning that we added enough chlorine so that there was 1.5 1.5 milligrams per liter of HOCl specifically. We were not adding 1.5 milligrams per liter of, let's say, NaOCl, which would then dissociate to HOCl and OCl minus, right? So what I was specifically saying is we had that much of HOCl. That means there's some separate amount of OCl minus, but we did achieve this. So with that in mind, the problem would go like this. To say, first of all, in a swimming pool, it's essentially a batch reactor. It's well mixed, no meaningful flow in or out. So that's what's telling us it's going to be a batch reactor. And our treatment level here is going to be 0.002. So we said 99.8%. We could say 1 minus n over n naught is equal to 0.998, right? Okay, so then we'll do our batch reaction dn dt. It's negative k c n to the 1 power. We can ultimately derive this to n over n naught equals e to the minus k c t. Okay, so then the question was how much time? We need to solve for time. So we just take the natural log both sides. We'll have natural log 0.002 equals negative kct, and then we just need to take the 1.5 milligrams per liter. The k from here, this is also in milligrams and liters, so that works out well. And then the time is in minutes here, so we'll recognize that that's going to be the time units. So we should ultimately get here 33.7 minutes. I think if there was confusion, it was probably to do with just the mass balance setup or possibly this point. But I think most of you had that right. So then part B was basically the same thing, but we're instead of using the HOCl, we're now going to use the HOBr. So same process. This time our K is 0.0098. And our time will end up being 422.8 minutes. Okay. So part C said what fraction of chlorine would be in the form of HOCl if the swimming pool had a pH of 7.8. So fraction in the form, so fraction of the total chlorine that would be in HOCl form. So what we're looking for is HOCl over the HOCl plus OCl minus. Right, that's the fraction that we're looking for. I think there was some confusion about that, a few of you. So if that might have been the entire confusion if you didn't do this correctly. We do know that the H plus concentration is 10 to the negative 7.58. Excuse me, 7.8. And so we can approach the problem by simply looking for a solution to this. We've done it a few times before. Technically, there's a few different routes you can approach it. Ultimately, we can get some relationship between the ratio of HOCl and OCl minus given the pH and the Ka coming from the other equation. So we could either simplify this or just simply start from the other direction, say Ka is H plus times OCl minus over HOCl. So here we can then get a ratio of OCl minus divided by HOCl equals Ka over H plus. Now, if I were to tell you that let's say I had a alcoholic beverage in my bottle. I don't. This is water. But if I were to tell you that 70% of it was water, okay, then I'm going to ask you what is, or let's say, let me rephrase that. Let me say I don't have a full liter, but I do know that I have 3 times as much water as alcohol in it. Okay, with that information, you could tell me the fraction that is alcohol, right? You should be able to reason that out and figure that out, right? It's not exactly the same as just giving you the ratio, but you know intuitively that you could figure that out. Well, that's what we're doing here. So if you have any confusion, if you're getting confused, okay, why are we doing this? Back up a step and say, oh, you have a ratio between 2 substances. That's what you get from this part of the equation. The other part is just figuring out how to get it into a fractional form. Okay, so if you do have any issues with this, just know that what I'm about to do here, you don't have to do it this way. You could work it out as like, oh, I know the ratio, therefore I can find the fraction. I could even say, let's pretend I have one mole total and say, well, that means 1 out of, if there's 4 parts total, one is HOCl, 3 is OCl minus or whatever. You can reason it out that way. That would be just fine. I find it's pretty simple to go ahead and divide the top and the bottom by HOCl here. So this will end up being 1 over 1 plus OCl minus divided by HOCl. And that's where the ratio comes in directly. And so we can put that in and then find our answer to be 0.355. Okay, next question is basically the same, except this time our Ka value itself was different, whereas the Ka here, you can take a look from the stuff up here. This was 2.88 times 10 to the minus 8. Of course, sometimes we'll give that to you as 10 to the minus 7.54. Different information sources will give it to you differently, but it's just a number, right? So I like the 10 to the something because it's a little simpler to relate to pH scale, but sometimes you won't get it quite in that form. Okay, so then with that, you get the ratio or the fraction. Do the same exact problem otherwise, except it's HOVR. And then here we should get 0.864. Okay, so part E then says, which disinfectant would you recommend for a swimming pool at a pH of 7.8 and why? And so I think everybody looked at that and just simply gave me an explanation about, given what you had just solved, usually you were thinking about, okay, which one has more of the H version, the HOCl or HOVR at pH 7.8. So some of you said, oh, well, the fraction here for the HOVR is better because we have that much of it. Some of you said, well, the coefficient of specific lethality is higher for chlorine, so maybe that's going to be the better one. So there was a few different answers, and I think I gave everyone partial credit. But the closer you got to, I guess the full answer here, which is what I'll say, is to look at essentially K star, right? K star for HOCl, that's going to be the concentration of HOCl in milligrams per liter times the K for HOCl, right? So that's K star, is those two multiplied by one another. And so if we take a look at a particular pH, we have this ratio here. What you could do is you could say, let's imagine, and it doesn't matter which which value you imagine, but you could say imagine 1 milligram per liter total with some value. So if you were to apply your disinfectant and you were going to afford 1 milligram per liter of that disinfectant, that's what I'm imagining here, right? So then we take a look at what fraction of that is the good stuff, the strong stuff, and go from there to see which one's actually going to be a better reaction rate constant for the entire equation. So just as a little side note, when we do the rate of change for our n, we're describing that as kc, the negative kc, and when we derive it, we'll have the time there. So in our equation then, k star, I guess we do have that. K star is k times c, right? So we need to include both of those if we have a pH dependence here, because that can matter. So the way I did it was I said, well, we have, let's say, 1 milligram per liter of something times the K for that HOCl times that fraction that we solved for. So I'm going to include that fraction here, 0.355. So the arbitrary part is the 1 milligram per liter here, but if you just simply multiply the fraction by this constant, assuming that you kept the same dose of chlorine or bromine, this should work out. So this here would give me a value of 0.044 per minute. So what I'm going to compare is the K star for both cases. K star for HOBR. Then, again, we're doing essentially milligrams of HOBR per liter times K HOBR times the fraction of HOBR that exists at that pH, 864. And here I get 0.0085 per minute. Okay, so there's a bit of subjectivity here in terms of what would be best for a swimming pool. Is it the fastest disinfection rate constant that you can have? Because in this case, the HOCl still wins even though there's a smaller fraction of it. So that was kind of ultimately the point I was hoping for you to arrive at, is looking at that K star, seeing which one was effectively higher. Now, maybe that means that it's less stable and it lasts a shorter amount of time, the chlorine altogether. So maybe practically speaking, it would actually be better to use HOBR. So I had some respect for answers that were kind of discussing, well, you might not actually need it to be super fast. You just want it to be there. If you gave me good reasoning, I was happy to entertain that. But the closer you got to this type of analysis to say, okay, well, overall, what's going to be the most effective? That's sort of what I was looking for. Okay. Does that make sense? All right. So part 2, problem 2, we say, let's consider a portable UV disinfection system to be used with a 5-gallon, 18.9 liter cooler with a lid. And so the setup will allow water to flow in the top and out a spigot at the bottom. And effectively, it acts kind of like a CSTR when we run it that way. If we have a disinfection rate constant for UV278 at 6.3 per second for E. coli, what is the maximum flow rate that the system can handle to achieve 99% inactivation? And I ask you to answer in liters per minute. Okay, so first thing I'll do here is draw our system. Got a kind of a cooler system with a light at the top, flow coming in, flow going out, and it's well mixed enough to call it a CSTR. We know the volume, 18.9 liters for a 5-gallon cooler. And we know our K is 6.3 per second. Now, before we even dive into any of the UV stuff, we ought to stop and think about, okay, this K that we have here, this is in per time units. And so that's sort of a net K. It's kind of like that K star that we were just dealing with. So we'll, later in the problem, we'll kind of distinguish between that K specific to the UV and the K here, but we'll get there in a minute. Okay, so this is going to be then a first order decay problem in the CSTR. We also know that we ultimately need a design value here that achieves n over n naught to be 0.01. So it's 1 minus removal would be 0.99, or excuse me, 0.01, right? That's 0.01. So the removal is 0.99. So 1 minus 0.99. Okay. So typical setup here would be assume steady state, so no accumulation of the bacteria or pathogen in the E. coli here. In the container, we have some flow coming in. We have some amount of E. coli coming in minus what's going out, Qn. Might be a good idea to go ahead and label these things. And then plus our reaction, which is a decay reaction in that volume. So that'd be VKN. And from here, we've solved this many times, so we can get that essentially to, well, we're solving for Q in this case, right? So it's going to be a little different. I'll just work from here to solve for Q, because a lot of times we've solved for n over n naught, but we already know that. So maybe it makes sense to solve in terms of n over n naught and then solve for Q, or I think in my notes I went ahead and solved for Q itself. So we'll go ahead and get the Q terms by themselves. I'll move VKN to the left side. Go ahead and extract Q from these two. So it'll be n naught minus n. We can divide both sides by that. So Q will be equal to VKN divided by n naught minus n. And from here, we can see that, well, if we divide the top by n and the bottom by n, we'll end up with a ratio of n naught to n, and that'll cancel to 1. So that'll actually get us very close to what we need. So this will be VK divided by n naught over n minus 1. Now, like I said, you could have just solved this for n over n naught like we often do, or n naught over n like we've done with the particulate matter, and done the algebra from there. I just happened to do it this way and looked for a way to get that in a ratio here. So if the removal, the amount remaining, let's say 1 minus removal is amount remaining, that's n over n naught, then we know n naught over n should be 1 over that, which is going to be 100. So then we can put that down here to say this is VK divided by 100 minus 1. Okay, so in that volume then, if we put that into liters, that's like 20 times 6-ish. So that, and then divide that by 99. Ultimately, we end up getting there a Q of, let's see, 1.2 liters per second. And then we need to multiply that by 60 seconds per minute. And we'll get 72.2 liters per minute. Okay. So algebra is a little different there than we've done in the past, but overall it's really the same process. And probably if you were concerned about anything, it might have been that you didn't recognize that this K that was given was simply the overall K there. Okay, so part B says if you decide to operate in the device in batches, so you stop the flow, you fill it up, you clean a bunch of water, and then you use it, maybe pour it out or whatever, and then fill up a new batch. Question is, how long should you wait to achieve a 4-log inactivation of E. coli? So you fill up a batch and turn it on, how long do you have to wait? That's kind of the premise here. So we know in this case, n over n naught is going to be 0.0001, so that's 4-log inactivation. And this is going to be, since it's a batch case, this is equal to e to the minus kt. So we just want to know time. So the natural log of 0.0001 equals minus kt. We can find time to be 1.46 seconds. Probably should have just asked for the answer in seconds, but I did ask for a minute, so that's 0.024 minutes. Okay, so very quick under these conditions. So one thing we can see is in order for a CSTR to achieve 99% removal, you have to be removing quite a bit of bacteria, or removing them rather quickly. Because it's well mixed, water instantly is escaping. You basically have to be diluting it enough so that as soon as that water comes in, you're diluting it so much that it's 99% reduced, right? So that's actually quite a low amount you have to achieve, given that flow rate that we were handling. Okay. So part C says, suppose a different microorganism has a coefficient of specific lethality equal to half that of the E. coli under this same light irradiation, the 278 nanometer light. Still operating in a batch mode, how long would you have to wait until you achieve a 4-log inactivation of this new organism? So what we're talking about is if K was 6.3 per second, well, we can break that into some coefficient of specific lethality times essentially the dose of UV that they're getting, right? Or maybe an intensity term. So you could say this is kind of like a K star equals K times C. And I think we had in the lecture notes, I think we wrote the coefficient of specific lethality like that times some intensity. The point being, we doubled this, right? So we have to, right? So it said the new organism has a coefficient of specific lethality equal to half of that under the 278. So that means the intensity stayed the same. We didn't change the light. We just halved some part of this. So we'll say K new then would be 1/2 times whatever was there before, right? Oops. Draw that. So we don't even need to know any information about them. We just need to know that it's half. So essentially then, that just means K is equal to 3.15. Half of 6.3. Okay, so then our question just simply becomes 0.001, natural log of 0.001 equals, and we can literally say that's 6.3 per second divided by 2 times time, right? So ultimately, we just do the same exact problem and double it. It's going to take twice as long. And so the time then is 2.92 seconds or 0.049 minutes. Okay. All right, so then problem 3, we had a sample of water at pH 9 containing 150 milligrams per liter of calcium ions and 60 milligrams per liter of magnesium ions. Part A said find the total hardness. And by the way, some of you might have noticed the last problem here, I recognized was not quite fair. I hadn't taught you a specific concept that I should have, and so I actually counted that as bonus points instead of counting it against you. So essentially, there were 15 points for part A and B, and then 5 available bonus points for part C. Okay, so anyway, for part A, find the total hardness in milliequivalents per liter. So we can describe that the hardness as essentially the calcium ion concentration, and I'm putting these in the parentheses, meaning that we're dealing with either milliequivalents or in the form of as CaCO3. Mg2 plus here. So these are the two primary contributors to hardness kind of anywhere you go. So we're going to need a few things. We'll need the molecular weight of calcium, that's 40 grams per mole. Molecular weight for magnesium is 24.3 grams per mole. The equivalent weights then for calcium and magnesium are going to be essentially those divided by their charge. So each of divided by 2, we'll get 20 grams per mole. Excuse me, not grams per mole. Milligrams per milliequivalent, or grams per equivalent. So it's milligrams per milliequivalent charge. Essentially, that's essentially moles of charge, by the way. That's why it relates to the per mole of the substance. And 12.15 milligrams per milliequivalent. Okay, so all of that in place. Now we can get our answers. Expressing the calcium, if we find calcium 2 plus here, the milliequivalents of that, it's going to be 150 milligrams per liter of Ca2 plus times, and we need to convert this from milligrams per liter into milliequivalents per liter. So we're going to multiply this by 1 over the equivalent weight. So that'll be 1 milliequivalent per 20 milligrams Ca2 plus. So here we're going to cancel the milligrams calcium and milligrams calcium, and so that should give us our answer here as 7.5 milliequivalents per liter. Okay. Same thing with the magnesium. Here we had 60 milligrams per liter of it. I'm going to multiply that by the 1 over 12.15. Again, that's the we can write it as milligrams per milliequivalent down here, or just move the milliequivalents up there. Okay, and that should give us a value of 4.9 milliequivalents per liter. So then the total hardness is the two added together, which gives us 12.4 milliequivalents per liter of hardness. Okay. So I think if there was confusion, I think it had to do with kind of the conversion here. If you track your units, that's probably going to help. And simply remembering that you need that equivalent weight and how to solve that. Okay, then part B says, okay, how about expressed as milligrams per liter of as CaCO3? So instead of milligrams of Ca, we're going to normalize both hardness values as CaCO3. So that requires us to take some X milligrams per liter of some substance and multiply it by 50, the equivalent weight for calcium carbonate, 50 milligrams CaCO3 per milliequivalent, and then divide this by the equivalent weight of X. That's going to be a milligrams X per milliequivalent. So if we take a look here, so we have milligrams X on top, milligrams X on the bottom. That's going to allow us to have the milliequivalents come on top. That milliequivalence then is going to cancel with this milliequivalence, and the only units remaining are going to be milligrams CaCO3 per liter. Okay, so that's how this equation functions. And so essentially, we just need to take the same types of calculations we did a moment ago and say, well, here the calcium 2 plus, when expressed as CaCO3, we send it through that process. That's going to be 150 times 50 divided by 40. Ultimately, that gives us 375 milligrams per liter as CaCO3. Now, might be worth taking a moment to think about this. We have 150 milligrams per liter of calcium ions. And so when we think about a calcium ion by itself, to express that as something that is larger and heavier, the CaCO3, that larger and heavier is going to have more mass per mole, right? And so if we had the same amount of calcium, that didn't change, but we're expressing it as if it were something else, that something else has to weigh more to get the same amount of calcium in there. That's might be helpful in terms of why this is such a much bigger number than the 150 milligrams per liter. And if we were to take a look at the ratio here, the atomic weight, Ca is 40, CO3 altogether is 60. So 40% of this is calcium. So if we divide 150 by 0.4, that probably gives us exactly 375. So just because, just for the sake of it. So if we take 150 divided by 0.4, there we go. Okay, so that's kind of what we did. In calcium's case in particular, it works nicely because calcium is literally in this thing. Of course, that's going to be different if we have different charges and all that. So we'll do magnesium through the same process. We should get 246.9 milligrams per liter as CaCO3. Then the total hardness should be those added, should be 621.9 milligrams per liter as CaCO3. Okay, so that leaves us with the last problem. I say find the alkalinity of the water expressed in milliequivalents per liter. And here's where, as I was grading and preparing the solutions, I realized I did not quite prepare you enough. There was one concept that I meant to introduce and didn't have slides for it. And so I would say I gave you a partial introduction, so it was, I didn't feel like it was fair to count against you, but I thought maybe you were going to be able to get some bonus here. So when we think about the alkalinity system, that acid neutralization capacity is, kind of one way to describe it. On the simple terms, alkalinity, for this problem in particular, is going to end up being Ca plus magnesium. So in a simple way, it's a very easy answer. In fact, we already derived that answer. But the reason that's true is what I didn't quite introduce. So we talked about alkalinity being, if we described the equation of it, we had often talked about it in terms of carbonate. And so we would say, well, this is going to be the CO3 2 minus, expressed as milliequivalents or whatever, plus the HCO3 minus plus the OH minus minus the H plus, right? So some of you were taking that form and were working with the OH minus and the H plus to see what you could do with that. And essentially what's going on here is we're achieving some sort of charge balance with these different species within the carbonate system. Ultimately, if we do a charge balance across the entire system, the key for alkalinity is you can actually separate ions that will change given changes in pH and ions that are not going to change. And so if you put all of one type on one side of the equation and all of the other type on the other side of the equation, you can get sort of an equilibrium there where you know that the Ca2 plus Mg2 plus ultimately have to be equal to, so stacking all the ions that we know about that cannot change if you change pH, those ultimately have to be the same or equivalent to the amount of negative charge that can exist by things that do change when you add pH. Because changing pH, it's going to affect some things but not others, right? So if we have calcium, magnesium, and we could even have chloride in here, right? We could say, if we had this in the system, we could say minus Cl minus. None of those should change when we do anything to pH. So we have the total charge of the ones that can't change should be offset by the total charge of the things that are changing, which would be the carbonate system, for example. Okay, so that's the concept I didn't really address directly, and so that's why I'm spending a minute to say it here. We could then say that's going to be this CO3 2 minus, but you don't have any information about this in this particular problem, right? We don't know anything about the carbonate system. You only know something about the OH minus and the H plus. Well, I guess we do know that we're at least expressing things as CaCO3, but yeah, so that doesn't help. Okay, so that means if we take our original alkalinity equation here to be that, set equal to the stuff that can't change based on the charge neutrality concept, that's how we can get to this as our answer. And we solved that earlier as 12.4 milliequivalents per liter. Okay, so if you gave me that and I could kind of see that you were doing something with charge neutrality, I probably gave you some bonus, just depending on how close you got to this type of a setup and description. So maybe you could have gotten there with the stuff we covered in lecture, but I never went all the way to put these dots together. So I definitely wanted to treat this as bonus instead of required. Okay, so I think we'll leave it there for the exam. Any questions outstanding or anything? Okay, so as usual, what I'm going to do is I will post this video with a specific link, and I'll post those slides for you. I think what I'll do also, just to put a stopping point here, is I'm going to stop and restart the stream.